Welcome back, students. In this video lesson, we want to go ahead and talk about the thermochemical equation. Now, up to this point, we've talked about internal energy, we've talked about work, we've talked about potential and kinetic energy being part of this idea of internal energy, we've talked about enthalpy, we've also talked about heat. And so, how does this kind of combine? How does it really work? Well, it all comes together in this idea of a thermochemical equation. And it's tied to this idea of enthalpy, or this idea of heat from within the reaction. Now, there is another discussion that we need to engage in with relation to this. And so let's just move over to the side. But it does branch, or it does kind of have its roots in this section here. Essentially, when you have a reaction, a general reaction would essentially be represented as follows. You have a little a plus B goes to form maybe C and D. And so here we can kind of break this down in terms of the reactants and the products. And essentially, if you're able to go in the one direction, it'll have a certain product. And you're going to be paying attention here to the various mole numbers A, B, C, and D. But the main thing here that we look at is whether we're forming bonds or whether we're breaking bonds. And so the idea here is if you have energy that is being absorbed, that's going to be energy that is then going to cause breaking of bonds. Okay? And so here the energy that is absorbed, and this is going to lead to bonds breaking. And on the other hand, if you have bond formation, this is going to be in terms of energy that is released. Okay, and so this here kind of gives you an indication of whether you're going to have something that is going to be positive and negative. And so here, if you absorb energy, this is going to be a Q value that is positive, and if it's energy released, this is going to be a Q value that's negative. This also can be interpreted as either an endothermic perspective, or it's going to be an exothermic, and I'll put this down here at the bottom for exo. Okay, and so this here is extremely important to us because when we have a chemical reaction, it allows us to understand if you have a Q value that's positive, you know that there was a lot of energy that actually went into that. And so bonds were being broken, or bonds were being broken because energy was being absorbed. And on the other hand, if bonds are formed, then that was a lot of release of energy, because obviously when you're forming bonds, that actually is going to lead to the more stable arrangement between atoms, and it's going to be a lot more stable for it. And what that really means is that the amount of energy needed to keep atoms in their own individual singular state is going to be requiring a lot more of an effort, a lot more energy to do that, as opposed to when you form, say, a diatomic molecule, or when you form a compound or a new compound. That particular arrangement is always going to be arranged in such a way that it takes the most stable form, which requires less energy. Any excess energy as a result of that rearrangement is going to be given off, and that's why we see exothermic conditions when that occurs. So what does this mean for us? Well, it means for us that how we kind of look at this particular section here in terms of whether we're going to take the energies that are needed to break the bonds, or if we're going to take the energies that are released, we can then look at this from the perspective of whether we have the energies of the reactants versus the energies of products. And this is going to be the basis of a later video we're going to deal with when we talk about the Big Mama equation, or Hess's law. Those are two different ways that we're going to look at this. But one of these methods here is essentially going to take the sum of the energies here in terms of products. And so we'll say here the energy, and we'll say the delta H of the products versus the delta H of the reactants. And the ultimate value here is going to tell you whether energy is going to be going in or going out. In other words, is it going to be endothermic overall, or is it going to be exothermic? So just to recap then, the overall reaction then here that we have in this section here is going to mean that for every combination of reactants, it will produce a certain amount of product, and then we can now then attach to it here a certain value with delta H. It'll have a very specific numeric value, and that number then is associated for a very specific mole ratio associated with the products and the reactants. And a couple of examples down the road here, when we start doing examples in some of the later videos, you're going to see that once we have a full balance reaction, we can then use stoichiometry to help us find the delta H value, or the heat of a reaction. And that's really what this is called here. And so let me just label this here. This here is called the heat of a reaction, which is also known as the enthalpy. So if you haven't already subscribed, please do so. Go ahead and keep watching, keep learning, and we'll see you in the next video.